Hi class, today's lesson is about Faraday and Lenz law. This is class by Raj teaching for Physics Semester 2 STPM. Hi class, today's learning outcome is to state and use Faraday's law and Lenz law. Electromagnetic induction is the production of an electromotive force across an electrical conductor in changing a magnetic field. Michael Faraday is generally credited with the discovery of induction in 1831, and James Maxwell mathematically described it as Faraday's law of induction. Lenz's law describes the direction of the induced current. Electromagnetic induction is also a process of using magnetic field to produce voltage in a closed circuit, a current. Equation in his theory of electromagnetism. Faraday was aware of the direction, but Lenz stated it so clearly that he is credited for his discovery. Electromagnetic induction law consists of a Faraday law and Lenz law. Faraday law talks about the magnitude of the induced EMF, whereas Lenz law talks about the direction of the induced current. In Faraday law, the basic quantity that we have to understand is the magnetic flux link with the conductor changes. The magnetic flux link with the conductor changes. When the magnetic flux link with the conductor changes, Faraday says an EMF is induced. And that induced EMF is proportional to the rate change of magnetic flux linkage. In Lenz's law, it is stated that the direction of the induced current must be that it opposes the change of the magnetic flux that induced the current. So if you look at this is an electromagnetic induction law. This is the induced EMF, and the negative speaks about the Lenz law. And this one talks about the Faraday law. Flux linkage, if you see this word here, magnetic flux linked with the conductor. Flux linkage is the linking of the magnetic field with the conductor of a coil when the magnetic field passes through the loops of the coil expressed as a value. Now class, before we go and use the application of Faraday law and Lenz law based on the example in Form 6, let's look at something which you have studied in Form 5. About Faraday law class. Faraday law is not something that is new to you. You have studied Faraday law before. Okay, when you were in Form 5, you have studied Faraday law. Okay, so let's flash back to what you have studied before. Okay, based on the example you have studied in your Form 5. Okay, now according to what you have studied before, Faraday law says that, okay, Faraday's law states that, number one, the magnitude of the induced EMF, okay, the magnitude of the induced EMF is directly proportional, to the rate of change of magnetic flux through a conductor. Okay, magnitude of the induced EMF is directly proportional to the rate of change of magnetic flux through a conductor. Okay, so now when you were studying in Form 5, you used this example. Okay, let me draw the figure here. We had iron yoke here. Okay, this is iron yoke. Okay, alright. Now, what did you understand with this? Here we have a north, we have a magnetic
here is north, permanent magnet, which is north here, and this is south. Okay, and then I think you are very familiar with this diagram. Okay, then we know there's a magnetic field line of forces that exists from the north to the south. Okay, all right, and the magnetic field strength is B. Okay, all right. So what happens here at the first, we also have one conductor, which I'm going to take another color, maybe green color. We also have one wire or a conductor which is fixed to a galvanometer. Okay, we also have that. Okay, so first thing, what happens? Number 1. Now we take the conductor, this conductor which is fixed through a galvanometer, we cut through the magnetic field B. Conductor, okay, fixed to a galvanometer. Galvanometer cuts through the magnetic field. Cuts through the magnetic field. Okay, it cuts through the magnetic field. So if this is the conductor, I take it and I cut through the magnetic field. So when you cut through the magnetic field, what happens is, number 2, the magnetic field strength will change. Magnetic field strength will change. Okay, so when I say the word magnetic field strength, I'm talking about B. B will change. So first it was B, right? First it was B. So when you cut through, what will happen? The magnetic field strength will change from B to B1. Okay, number 3, then we see that when the magnetic field strength changes, when the B changes, what will happen? The magnetic flux will change. Why the magnetic flux change? Because magnetic flux equals to BA. So when B change, magnetic flux will change. Okay? So first it was when it was B, the magnetic flux was phi. Okay? Then it changed to B1, so the magnetic flux is phi 1. So it changed. From B to B1 changed, so phi to phi 1 changed. So it changed from phi to phi 1. Okay? Then according to Faraday, number 4. According to Faraday, he said what? He said when the magnetic flux change, okay, I'm going to write it with the blue pen. He said when the magnetic flux change, according to Faraday, he said an EMF is induced. An EMF is induced. Okay, so here if you look at this, what Faraday says, magnitude of the induced EMF, okay, magnitude of the induced EMF, okay, is directly proportional to the rate of change of magnetic flux through a conductor. Okay, that means when the magnetic flux changes, an EMF is induced, and the induced EMF is directly proportional to the rate change of magnetic flux through the conductor. Okay, all right. Okay, so now there's an EMF that is induced. EMF is induced. So induced EMF means there will be a current that will be induced. Okay, current will be induced. That means we call it induced current. Induced current. Now where is the induced current will be formed? The induced current will be formed in the conductor here. So current is induced, Okay, so I put it this way. Current is induced in the conductor. Okay, current is induced in the conductor, and then when there's a current induced in the conductor, galvanometer detects it. Galvanometer detects it. So this is what you have studied in your form 5 about Faraday law. Okay, so Faraday says, alright, magnitude of the induced EMF, which is the E. Okay, magnitude of the induced EMF, which is the E, okay, is directly proportional to the rate of change of magnetic flux d phi over dt through a conductor. So you see, we can know the induced current, induced EMF will have induced current, and the induced current, we will, galvanometer can detect the induced current. Okay, so we look at the keyword in this situation here. The keyword is cuts through. Cuts through means there must be motion. Cuts through. Okay, there must be motion. Motion that is cuts through the field. That means motion that changes the field. Okay, motion that changes the field, which is the magnetic field strength. Okay, then what will happen? Magnetic field strength will change. B will change. When B changes, what will happen? EMF is induced. When EMF induced, what will happen? Current is induced. Okay? Okay, if B change, phi also will change. Magnetic flux also will change. Okay, when phi also will change, and then EMF is induced, current is induced. So this is for what you have studied in your form 5. To apply the Faraday law into an example which is a solenoid. So we're going to look at a solenoid. So I have a conductor which is a solenoid. Okay, fixed to a galvanometer. Fixed to a galvanometer. Okay, then I have a bar magnet. Okay, where the bar magnet, this is north, this is south. So I have a magnetic field around the bar magnet from the north to the south. Okay, so it looks like this. So the magnetic field is B. I'm going to label it as B. Okay, alright. So now we're going to apply Faraday law. So what happens first? Okay, when the bar magnet is pushed in, when the bar magnet is pushed in, okay, what will happen? When the bar magnet with the field is pushed into the solenoid, okay, what will happen is the conductor will cut through the magnetic field. Okay, the conductor will cut through the magnetic field B. It will cut through. So the more you push in, the more number of coil will cut through the magnetic field. Okay, so when the bar magnet is pushed in, the magnetic flux linkage. Okay, I use the word linkage is because it is a n turns of coil. So magnetic flux linkage, okay, of the solenoid will increase. Agree? The magnetic flux linked with the solenoid, or magnetic flux linkage of the solenoid, or with the solenoid, okay, I prefer to use the word with the solenoid, will increase. Now, why is the magnetic flux linkage with the solenoid will increase? Okay, now why this happens? Increase. Why? Because we know magnetic flux linkage is equals to NBA. Okay, is equals to what? NBA. When you pushed in the bar magnet into the conductor, into the solenoid, what will happen? The number of turn that cuts through the magnetic field will increase. Okay, the number of turns cut through the magnetic field will increase. So that will increase the magnetic flux linkage. And when the magnetic flux linkage increase, EMF will be induced in the solenoid. EMF will be induced in the solenoid. Okay, so EMF induced means it's like a kind of a voltage that is induced inside the solenoid. So when the EMF induced in the solenoid will cause a current induced in the solenoid. Okay, current will flow. An induced current will flow in the solenoid, and galvanometer will detect the current, the induced current. Now, to know the direction of the induced current, we need to use Lenz law. We need to use what? Lenz law. So this process is a Faraday's process. Okay, it's based on Faraday law. So Faraday law is EMF induced is directly proportional to d phi L over dt. Now, why is it d phi L? That means magnetic flux linkage is based on our example. Okay, so this is based on our example because here got a lot of number of turns of coil, so we use magnetic flux linkage. Okay, now let's see what the book has to say. Okay, the induced EMF caused an induced current in the conductor. The direction of the induced current is given by Lenz law. Okay, alright. When the north pole of the bar magnet, okay, now let's look at this together. When the north pole of the bar magnet is pushed, okay, into the end of the solenoid, okay, the magnetic flux linked with the solenoid increases. Okay, magnetic flux link with the solenoid increases. Okay, magnetic flux link means is magnetic flux linkage with the solenoid increases. Okay, so then what happened? According to Faraday law, the change in the magnetic flux induced an EMF. And induced current flows in the solenoid. So that is based on Faraday law. Okay, alright. Knowing what is Faraday's law and Lenz law, let's look at these two examples class, okay, where we're going to emphasize on understanding Lenz law in this example. Okay, what we have studied under Faraday law is that when the bar is pushed in, okay, when the bar is pushed in, what will happen is the coils, okay, the coils or the conductor will cut through the field. Cuts through the field. The conductor will cut through, the solenoid will cut through the field, the magnetic field. Okay, so once when the conductor cuts through the magnetic field, what will happen is magnetic flux linkage will increase. Okay, there are two ways of looking at this magnetic flux in linkage increase. Okay, we can understand it by two ways. One way is we know magnetic flux linkage is equals to NBA. One way is the magnetic flux linkage increases because as we push the bar into the solenoid, the coils that cuts through the magnetic field increases. So therefore, the magnetic flux linkage increases. Or we can say, as we push the bar magnet inside in, the magnetic field, okay, the magnetic field increases. So once when the magnetic field increases, okay, so the magnetic flux linkage increase. Now, when they say the word increase, that means it's a change. It's a what? It's a change. Okay. So when it is a change, what will happen? Faraday says an EMF will be induced. Okay. EMF will be what? EMF will be induced, which I'm going to label the EMF as capital E. Now, once when the EMF is induced, this EMF is like a voltage. Okay, a voltage that exists inside the solenoid. What will happen is current will induce. Definitely when there is a EMF, there will be a current, and this current is a induced current. Okay, and this current that is induced, it has a direction. Okay, and the direction is actually, we have to know how to apply and find the direction is by using Lenz law. Okay, now let's come to this. When once there's a current induced, then there's a magnetic field that exists. Another magnetic field that is exist. Okay, all right. So here again, a EMF is induced, a voltage is induced, therefore there must be a current that is induced. Once when there's a current that is induced, that means there's a magnetic field that exists. So Lenz law talked about this. When you look at the definition from our textbook, he said that the direction of the induced current is such that it produces a magnetic field to oppose the change in the magnetic flux that induced the current. Okay, so what does it mean is that the magnetic field that exists or that induced is a field that will oppose to the change. So when it opposes to the change, okay, it opposes to the change. Okay, opposed to the change, and the change is increased. So when it opposes to the change, so it will form a magnetic field to decrease. Okay, to decrease. Now you need to push in to increase. So now in order to decrease, we need to push out. So in order for that to push out, the magnetic field that is formed here will be north. So if north and north, they will repel. So it's like pushing it out. It's like pushing the bar out. So here will be south. Okay, here will be north, here will be south, and then you draw the magnetic field. It will be from the north to the south. Okay, okay, so this will be the magnetic field that was induced due to the current induced. So what will happen is when the bar magnet goes, this Lenz says the magnetic field that is formed will oppose the change in the magnetic flux that induced the current. Okay, so then it will push out the bar magnet. It will repel. Push out means it will repel the bar magnet. Okay, so let's look at this. Okay. Okay, according to the Lenz law, the direction of the induced current must be such that it produces an effect which opposes the increase in the magnetic flux. The effect is produced when the induced current produces a north pole at the end A of the solenoid to repel, that means to push out the incoming north pole of the bar magnet. Hence, the direction of the induced current is as shown. Okay, so once when you already know the field, this is the north and this is the south, you are supposed to find the direction of the induced current by Lenz law. You use your right hand rule, okay, which is in solenoid, your right hand rule. This one will be the north direction, north will point towards north, and this one will point towards the induced current. Okay, so if this is my right hand, so this is not the direction of the induced current is like this. So if I hold the solenoid like this, okay, this is the solenoid. If I hold it, it is in this direction. So you can, vice versa, you can get the direction that the book has drawn. Okay, all right. Same manner, if you look at this example, all right, what happens? Okay, let's do this. What happens? Now, the bar magnet is pushed out. Okay, you pull it out. The bar magnet is like this, you pull it out. Okay, so the bar magnet is pushed out. Okay, push out. Okay, when the bar magnet is pushed out, what will happen? Okay, what will happen? When the bar magnet is pushed out, what will happen is magnetic flux linkage will decrease. Okay, when the word decrease means here means, that means is a change. Decrease means there is a change in the magnetic field. Okay, so this magnetic flux linkage that decreases, what will happen is an EMF will induce according to Faraday law. EMF is induced, and that EMF induced will induce current. Current is induced, and that current that is induced, what will happen is a magnetic field will form. a magnetic field that oppose the change according to Lenz's law will exist. Oppose the change will exist. Okay, so oppose the change. So now the change is to decrease. It oppose the change, the field that will increase. So in order to increase the field, what will happen is oppose the it is pushed out, so it will try to attract. It will try to attract. It's trying to push in, so it will try to attract. So in order to do that, the magnetic field will be from, this is south and this is north. Okay, this is south, this is north. So when this is south, this is north, and then after that you use a right hand rule. This will point to the direction of the north, and then this will point to the direction of the current. So you will notice the current is in this direction, same as the book. Okay, so when the induced current is formed inside the solenoid, you can see that the galvanometer is actually deflecting. If it is pushed in, the galvanometer deflect this side. If it is pushed out, the galvanometer deflect the other side. Okay, alright. So that is what Lenz's law is about. Okay, similarly, when the north pole of the bar magnet is pulled out of the solenoid, okay, magnetic flux link with the solenoid decreases. Okay, according to Faraday law, the change in the magnetic flux linkage induced an EMF in the solenoid. Okay, an EMF induced is formed in the solenoid. Now, the direction of the induced current must be such that it produces a south pole at the end A of the solenoid to attract the outgoing north pole of the bar magnet. So the direction of the induced current is as shown in figure 17.3. Okay, alright, so that is about Lenz's law. Lenz's law is consistent with the principle of conservation of energy. Okay, Lenz's law is consistent with the principle of conservation of energy. Okay, what did the thing says? The electrical energy, which is the induced EMF, is produced during electromagnetic induction is from the transformation of mechanical energy. Now, what does that say? Now, in this situation, the mechanical energy will be what? Okay, you have a solenoid which is fixed to a galvanometer, and then there is a bar magnet. This is north, this is south. When you push in the bar magnet in, okay, with a speed of v, so that means there is a mechanical energy which is the kinetic energy. So the kinetic energy, the transformation of the kinetic energy, which is the mechanical energy, okay, now will make an electrical energy produced, okay, which is the induced EMF. So if you look here, according to the Lenz's law, the direction of the induced current in the solenoid is such that it produces a north pole. Okay, now here, work done. In order to talk about energy, we have to talk about work done. And work done is energy. In order to have work done, we need to have a force. So in this case, based on this example, the first example, the force that was involved is a repulsive force. So work is done against the repulsive force, okay, between the north pole of the bar magnet and the north pole at the end A. Because when here, this is north pole and this is north pole, work is done against the repulsive force, okay. And we know that the work done is actually equals to energy. Okay, so the work done is transformed into electrical energy, where electrical energy is induced EMF.
Our second learning outcome for today's class is to find the EMF induced in a linear conductor. We need to derive and use the equation, and this is one of the examples of how to apply Faraday and Lenz law.
Let's look at EMF induced in a linear conductor. Okay, in a linear conductor. Alright. Now, figure 17.4 shows a straight conductor of length L. So we have a straight conductor of length L being moved. Okay, being moved. So there is a motion. Being moved means there is a motion at a constant velocity. So there is a motion being moved across a uniform magnetic field B. Okay, So now what happened is that if you look at this, the direction of the magnetic field is into the pitch. Okay, the direction of the magnetic field is into the pitch. Okay, is into the pitch. Alright, so the conductor, which is the length L, okay, it is moved. It is moved. So it cuts through the field. It cuts through the field. Okay, so when it cuts through the field, the magnetic flux changes. Okay, magnetic flux changes. And when magnetic flux changes, what will happen? In EMF is induced. Okay, alright, so EMF is induced. Okay, now suppose that the time taken for the conductor to be displaced at a distance x is t. Okay, so this is the v, which is the constant velocity. Okay, alright, so we have the motion. Okay, then we have the b. Okay, the b that changes. Alright, okay, and then we have the induced EMF. Okay, I'll tell you why I'm categorizing all this quantity. Okay, magnetic flux linked with the conductor. Now here is linked. Linked means the magnetic flux linked with the conductor means it is actually this is the magnetic field. So it is the conductor is in the presence of the magnetic field. Okay, so magnetic flux linked, not linkage, linked with the conductor. So we know phi is equals to B times A. Okay, B times A. So the B is in what position? The B is into the page, and then the area, surface area is facing here. Okay, is facing. So that means it's normal. Okay, it's normal. So we have phi equals to BA, and what is A? A is Lx. Okay, and then EMF is induced because of the cutting through the magnetic field. So negative d phi over dt, and then we substitute this one inside here, and we get E equals to negative BLV. Okay, alright, so here they said magnitude of the EMF induced. So they want the magnitude, so the magnitude will be E equals to BLV, where the negative is actually is by Lenz law. Okay, which oppose. Alright, okay, in general, the expression for the induced EMF E in a straight conductor, okay, application is in the straight conductor, a length L moving with a velocity V in a magnetic field is given by the vector equation is this. So that's why I was stressing on the word here, motion. When we have a constant velocity, we have moved at a constant velocity, it speaks about the motion. And then we have the B. Okay, because EMF is induced because of the change of the magnetic field. Correct or not? The rate change of the magnetic flux. Alright, magnetic field will change the magnetic flux. Alright, so therefore we have E equals to LV times B. Now, in order to find, okay, in order to find any of this, we can use Fleming right hand rule. So if you take the right hand, okay, Fleming right hand rule. Okay, now according to the book, okay, right hand, alright, this one is represented with velocity. This one is what? Velocity. Okay, so I'm going to draw like that. Why this? Like that and like that. So this one is represented with velocity, and then this one is represented with B, and this one is represented with the induced EMF. Okay, so according to the book, it is like this. Alright, okay, so direction. So if I use the example here, I use my right hand, the velocity is on top. Okay, the B is here, the E is here. You look, use the Fleming right hand for this example. Okay, alright, okay, now, but what I'm going to do is that I'm going to use another kind of way, which I'm not going to follow the book. I'm going to use this velocity as motion. The B is the B, which is the field. the magnetic field. And then this direction I'm going to use as induced current. So instead of I put velocity B and induced EMF, I put motion, I put B, I put I. So I get MBI. Motion, okay, like say for example this one, the motion is this side, okay, is this side. The B is into the page, okay, the B is into the page, so the induced current that is formed will be in this direction. So the induced current that is formed in the conductor will be in this direction. So MBI, okay, M, motion, it's because the conductor is pushed to this side, right? So motion, B is into the page, and the direction of this is the direction of the induced current. So that is what I will be using, because it's very familiar for me and I find it a bit easier. But in case if you don't want to use MBI, you can use this, okay, velocity. They are the same, okay, they are the same, okay. Alright, so
Our third learning outcome for today's class is to find the EMF induced in a rotating coil. We need to derive and use the equation of the induced EMF, another application of electromagnetic induction law.
look at EMF induced in a rotating coil. So what they want us to know, the learning outcome, is to derive and use the equation of the induced EMF. So you have to know how to derive, correct? Okay, so if you look at this, figure 17.6a shows a plain coil of N turns. Okay, we have a plain coil of N turns, each of area A, and in a uniform magnetic field B between the poles of a magnet. So we have a pole of a magnet here, which is south, and this is north, and then we have N turns of plain coil, okay, area A in a uniform magnetic field B. Now, initially, the plane of the coil is perpendicular to the magnetic field. Okay, the coil is rotated at a constant angular velocity omega. So it is like this. Okay, we know that there is a magnetic field here, okay, which I'm going to just take the diagram here. Alright. Okay, so we have here a magnetic field which is from the north to the south. This is the magnetic field which is north to the south. Okay, and it's B, and then it's uniform. Okay, it's B and it's uniform. The plane of the coil is A, and there's number of turns. Okay, now the coil is rotated at a constant angular velocity omega. So first the plane of the coil is like that. Okay, so if I put it in this diagram, then the coil is rotated at an angle of theta. So the coil is rotated at an angle of theta. Okay, so when the coil is rotated at the angle of theta, if we have learned our circular motion concept, we know omega is equals to d theta over dt. So theta is equals to omega t. Okay, theta is equals to omega t. Alright, okay, so that is one thing lah. So why we get a omega t? So the angle is omega t. Another one more thing is the direction of the magnetic field is in this direction. Okay, and then the plane, the direction of the plane, okay, if we solve this, I'm going to take a red pen. Okay, here is theta, so this is the plane, area is A, so here will be A sine theta, and then here will be A cos theta. Okay, so we must take the area, the direction of the area which is normal to the B. So the B is like that, so we must take the area also in this direction. So we take A cos omega t. So we know the magnetic flux phi is equals to, and since there's a number of plane coil of number of n turns, so we know this is a magnetic flux linkage. We know that phi is equals to NBA, where NB we use A cos theta, which is A cos omega t. Now why we use A cos omega t? Because A cos omega t is the one that is normal to the B. Okay, the B and the A cos omega t, they are normal to each other. Okay, all right. So now, next. Now at time t, the angle turned through the coil is omega t. Okay, at time t, the angle turned through the coil is omega t. Now magnetic flux link with the coil. That means it's magnetic flux linkage, which is this is a magnetic flux linkage. Okay, magnetic flux linkage. Okay, so we get NBA cos omega t. Now, what happens is, class, alright, if you look here, the field is in this direction, this is the coil. Okay, so the surface area which is normal to the field will be A cos omega t. The surface area which is normal to the field will be A cos omega t. So in order for induced EMF to be induced, what has to happen is the coil have to cut through the field. The coil has to cut through the field. And the way how to cut through the field is by rotating the coil. Then only EMF can be induced in this example. So that is the reason when the coil is rotated, okay, the coil is rotated, it cuts through the field, it cuts through the magnetic field. Faraday says there's a change of magnetic field and there's a change of magnetic flux linkage, then EMF is induced. So the induced EMF is E equals to negative d phi over dt. Okay, and we substitute the phi and then we get NBA cos omega t. Okay, alright, so I'm going to just write here. Okay, according to Faraday, a EMF will be induced if there is a change of magnetic flux. So in this case, it's a magnetic flux linkage. So negative d phi over dt. And what is phi? Phi is NBA cos omega t. NBA cos omega t. So we get negative d over dt NBA cos omega t. Okay, so then we differentiate this. We get NBA omega sine omega t. Okay, so and if you compare this is the induced EMF. If you compare this, then this is actually the maximum value. Okay, because it's a sine graph, so what is in front is the amplitude, which is the maximum value, which will be E naught, the maximum induced EMF. So you get E equals to E naught sine omega t. You get this. Okay, alright. So NBA omega is the peak of EMF. That means peak means is the maximum EMF. Okay, alright. So now let's look at the graph. Okay, let's look at this graph. Okay, if you look at this graph here, right, the EMF induced is alternating. Okay, so if you look at this, now we realize here, alright, the first thing is the equation is, the first thing is number 1, E is equals to E naught sine omega t. Okay, E equals to E naught sine omega t. Okay, alright. So now the coil is like this. It's at 0, correct? Okay, it's like this. So your omega t is 0. Your omega t is 0. position number 1. So sine 0, you get 0. So therefore E is equals to 0 when the coil is in this position. Okay, now when the coil goes, okay, if I draw like this, this is the B, this is the B, this is the B, okay, this is the B. So now the coil is like this, okay, 0. Okay, so it says when it's like that, the EMF induced is 0. That is logic, because why? The coil did not cut through any magnetic field. So when it doesn't cut through, there's no motion, so EMF it doesn't been induced. Okay, now the coil cuts through. It moves from this position, it moves to 90 degree. So it's cutting through the field. When it cuts through the field, what happened is EMF is induced, because when it cuts through the field, the magnetic flux linkage change, because the field changes. The B change, magnetic field change, and then magnetic flux linkage change. So when magnetic flux linkage change, EMF will start to be induced. So EMF will start to increase. Okay, it will start to be induced. It will increase its value until it reach maximum, until it's 90 degrees. Okay, that is the way of physics. But if you want to use maths, we can just put number 2, E is equals to E naught sine omega t, means sine 90. Sine 90 is 1, so you get E is equals to E naught, which is the maximum. So that's why when 90 degrees, induced EMF is from 0 to maximum. 0 to maximum. So induced EMF increases from 0 to maximum. Okay, increases. Let I write that. 0 to maximum. Okay, alright, so this is what happens in the first process. Okay, now the second process is, alright, what happens is, now the coil is like this. Okay, the coil is in this direction now. Now the coil again, it cuts through the magnetic field. It cuts through. What happened? It cuts through the magnetic field, but the induced EMF at this position here, which is 180, number 3, E is equals to E naught sine 180, you will get 0. So that means induced EMF from maximum decrease to 0. Induced EMF from maximum decrease to 0. From 90 to 180. Okay, so you get the graph like that. Alright, now next what happens? Now the coil is like this. Okay, now its first position here, okay, we have here the B. First position, it was like this, then it was like that. Now it's going back in the opposite direction. Okay, it's going back. So what happens is, alright, so it is now like this. So it's cutting through the coil from here to here. It's cutting through the coil. So when it cuts through the coil from 180 to 270, so you realize that the EMF increases from 0 to peak. From 0 to peak. From 0 to peak, it increases. 0 to peak. Okay, this is the peak. Alright, okay, then what happens? Now it's already here. Okay, so it cuts through the field, and then from maximum, okay, from EMF decreases, induced EMF decreases from maximum to 0. From maximum to 0. Okay, alright, so that is what happens. So if you look at the diagram, okay, this one is increase from 0, here it increase, and then after that decrease, then increase in the other direction, this side, and then after that it goes back to 0. It decreases back to 0. So it's a sine graph. Okay, so if you look at the graph, what can you say? You can say the EMF is maximum. Okay, first thing what you can say, the peak is NBA omega. So you see the peak here is negative NBA omega. Okay, Alright. Then you can also say that the EMF is maximum. Okay, you look at the EMF and it's maximum when, look at the diagram. Is maximum when the coil is, the plane of the coil is parallel to B. So this is the direction of the B. This is the direction of the B. So the plane of the coil is parallel to B. Okay. Alright. Then you will realize another one. EMF is 0. EMF is 0. Okay. When the plane of the coil is perpendicular to the magnetic field. So this is the magnetic field, this is the plane of the coil, perpendicular. This is the magnetic field, this is the plane of the coil. This is the magnetic field, this is the plane of the coil. Okay. Alright. So that is about graph. Okay. Alright. So next. Okay. The EMF induced in a coil rotated about an axis perpendicular to a uniform magnetic field is the principle by which the AC generator operates. AC stands for alternating current. Generator operates. Okay. The slip ring of the AC generator enables the coil to be rotated in the same direction. Okay, this is because the same end of the coil is in constant contact with the same carbon brass. So they're talking about this slip ring. Okay, this one, the effective value I'll be teaching in the next chapter, in chapter 18. Okay, all right. Thank you.